Welcome to the Deep Dive. Today we're going into a topic that's really at the heart of the entire robotic revolution. And we're not talking about the sci-fi stuff, robots taking over the world. We're talking about something more fundamental. We're talking about how they learn to feel it.
Right.
Because robotics is seeing this truly explosive growth. It's moving way beyond those old factory floors.
It really is. We're seeing it in places that demand incredibly subtlety, like high-precision healthcare, even entertainment.
Exactly. And there's this huge gap you need to understand between a simple automated machine, one that just repeats a blind motion, and a truly intelligent, responsive robot that can adapt.
That's the key distinction.
So our mission in this deep dive is to give you a shortcut, to get you straight to the secret ingredient that makes these modern machines, especially the collaborative ones, the cobots.
What makes them so precise and safe?
Yes, what makes them effective. And that secret ingredient, it's all about the technology of force measurement.
And what's so fascinating is just how broad the applications are. But the core need is always the same. I mean, robotics is expanding into manufacturing, healthcare, agriculture, entertainment, aerospace, you name it.
All of them.
And it all relies on one fundamental stream of data: reliable physical feedback. If a robot can't sense what it's touching, or how much resistance it's getting, it's essentially operating in pitch darkness.
That's a great way to put it, just relying on sight and scripts.
Exactly. This reliable force sensing is probably the biggest single enabler behind this recent leap forward. It's what tunes a powerful machine into an intelligent partner.
I love that analogy. Working in the dark, it just crystallizes the problem perfectly. Okay, so let's unpack that. If we want a robot that's delicate enough to, say, pick a ripe tomato without crushing it, how does it move with what we'd call intention instead of just brute force?
Right. How does it know when to push and, maybe more importantly, when to stop? The answer is that we have to give the system an internal sensory layer. You can think of it like creating artificial nerves, a sense of physical self-awareness. It's a concept we call proprioception.
Proprioception, okay.
Yeah, it's that internal sense you have where your arm or your leg is in space, even with your eyes closed.
So I know my hand is raised without looking at it.
Precisely. And for a robot, this means it needs to know three things at once: how much force it's applying, where that force is going, and how the environment is responding.
So it's an awareness that comes from physical feedback, not just cameras.
Exactly.
So what are the actual tools here? Are we talking about something like a simple scale?
Oh, it's far more specialized than that. We're talking about a whole suite of sensors. For simple measurements, you have things like load cells and even miniature load cells for really tight spaces. Then you've got torque transducers, which measure rotational stress.
So like the twisting force at a joint.
Exactly.
Yeah.
But the real game changer, I think, is the multi-axis sensor.
Why is that one so important?
Well, because the world isn't flat, right? A robot arm doesn't just push straight down. It might be twisting, pulling, shearing, all at the same time.
And a single axis sensor would just miss most of that.
It would miss almost all of that critical data.
Yeah.
So a multi-axis sensor is basically giving the robot a 3D sense of touch.
That's incredible.
Yeah, they're often placed at the wrist or the gripper, and they can map both tension and compression, along with those other forces, across several axes at the same time. And all this data, from the grippers, the joints, it lets the system detect tiny overloads before they become catastrophic. It's the foundation of physical decision-making.
And that immediately makes the machine operationally aware. It's not just a fixed program anymore, it's dynamic. If you want a perfect example of where this kind of precision is just absolutely non-negotiable, look at animatronics, the world of storytelling.
Oh, that's a fantastic example.
Right. When robotics meets storytelling, like for a film or a theme park, the movements have to be believable. Brute force just looks clumsy. It ruins the illusion.
It's a mechanical failure, but it's also a failure for the audience. And what's so interesting about animatronics is how it pushes the limits of that fine motor control. I mean, think about robotic face trying to show surprise, or a creature that needs to gently grasp something.
Right, without breaking it.
Exactly. So those sensors are detecting the exact pressure or strain on every single actuator: a finger, a jaw, an eyeball mechanism. And this real-time data means the engineers aren't just preventing damage, they're actually refining the performance of the motion.
So they can fine-tune it in real time.
In real time. They can adjust the grip strength, fine-tune the resistance in a joint to feel like real muscle tension, and just get this incredibly smooth, controlled motion.
Which really shows that this isn't just about function, it's about the quality of the interaction. So is the precision needed for a lifelike creature the same as what's needed for, say, industrial safety?
Fundamentally, yes. It's the same underlying mechanism. And when we generalize the benefits from, Hollywood robots to a sterile operating room, we find three major advantages. First is enhanced safety. By detecting excessive forces or unexpected collisions, the system can react instantly.
So if a human hand gets in the way?
Precisely. It's detected by a physical change in resistance, and the robot can pause or pull back way faster than a human supervisor ever could. It's not waiting for the program, it's sensing an event.
A self-preservation response.
Exactly. The second benefit is improved performance. That constant feedback lets the motion control systems fine-tune themselves.
So it gets better over time.
It gets better, more efficient, and the accuracy is measured in microns, not millimeters.
Wow.
And third, and this is maybe the most sophisticated part, is dynamic control. When a robot knows the precise torque on a servo or the strain on a gripper, it moves away from rigid programming. It starts making real-time decisions.
So it can actually feel the difference between a loose bolt and a tight one.
That's it. You can learn to feel the difference between something fragile and something robust.
Now let's talk about the scale of this, because this isn't just improving old factories. It's driving massive market growth. I mean, the numbers are staggering. Professional service robotics alone are projected to surge into the tens of billions of dollars pretty soon.
And that growth is really anchored in these high-value manufacturing regions. You see industrial robotics tied to sectors like automotive, aerospace, advanced electronics.
The big ones.
The big ones. And in places like Japan, China, Germany, and the US, where efficiency and quality control are everything, the demand for these sensory-equipped robots just dictates the market.
And in those industrial environments, it seems like these force sensors play two very distinct roles at totally different times. Can you clarify that for us?
Absolutely. In an industrial setting, you can think of these sensors as having two jobs: testing and actuation.
Okay, testing and actuation.
For the testing role, this happens long before the robot is ever on the line. This is all about quality control. Engineers use sensors to verify components, to do stress testing. They'll cycle a new joint under maximum load 1 million times to find its exact failure point.
So this is about building a better, safer robot from the very beginning?
Precisely. Then you have the actuation role. This is their job during real-time operation. Here, the sensors are the active feedback elements. They're the artificial nerves.
They're live.
They're live, constantly measuring resistance and telling the robot how to adjust its speed or pressure right now. So think about the difference between a script that says, push with 10 newtons of force, versus a feedback system that says, I feel 10 newtons, but the material is bending, so I have to immediately reduce to 5.
That is a world of difference.
It's the power of actuation data.
That makes perfect sense. Testing is for quality before, actuation is for performance during. Okay, let's pivot to the type of robot that really defines the future of work. The cobot.
The collaborative robot.
Right. And this is where accuracy stops being about efficiency and becomes a non-negotiable safety mandate. The big difference is that traditional industrial robots are huge, powerful, and they're kept in cages.
Fenced off from people for good reason.
But cobots are the opposite. They are designed to share a workspace with humans.
And that collaboration is incredibly complex. It's not just sharing space, it's handing off components, assisting with repetitive tasks, adapting to a human's variable speed.
Which means things can't be perfectly predictable.
Not at all. And because of that human proximity, the force sensing has to be exceptionally accurate. The sensors let the cobot instantly detect human contact, even a light brush, and halt.
So it's not just about avoiding a crash, but any unwanted contact.
Any contact. They regulate their grip strength, they actively avoid pinch points by sensing joint strain, and they have to react properly when something unexpected happens.
So it sounds like the real intelligence in a cobot isn't just the programming, but its ability to process that force data instantly and put safety first.
It's absolutely in its ability to process that tactile sensing data and make a dynamic decision to say, this strain is outside the safe range, I must stop now. That human-friendly level of force feedback is what enables this whole idea. The future of work won't be humans versus machines.
With humans and machines working together.
Collaboratively, enabled by this deep sensory awareness that really it mirrors our own sense of touch.
And that brings us to our core takeaway for you today. Yes, robotics is driven by powerful motors and very sophisticated software. That's a given. But the genuine breakthrough, the real shift from just automation to actual intelligence, is powered by that constant stream of precise force data.
From load cells, torque transducers, and those critical multi-axis sensors.
That data is what gives these machines their awareness. It transforms them from blind tools into, well, efficient and human-friendly partners. And this technology is fueling more capable machines everywhere, in surgical suites, on assembly lines, and even in agricultural systems. The ability to feel is really the ability to interact intelligently.
And as we wrap up, here's a thought to consider. If these miniature high-precision force sensors are absolutely necessary for a robot to safely work with a human in a factory, what other unexpected applications could they enable?
Outside of industry or entertainment?
Right, think about tasks in the near future that require that same delicate, responsive interaction. Things that we humans currently rely on, just pure intuition and a gentle touch to get right.
Something to think about as this revolution continues to move from brute automation to, well, intelligent feeling machines. We encourage you to explore the applications of this technology because that data is truly shaping the world around us.
That's all for this deep dive.